It's a real pleasure and honor for me to present this lecture that I called The Quest for the Ideal Glass. So we all know what a glass is. I'm drinking water right now from this glass. I have next to me a plastic ruler, which is made of a polymer glass. And if I look outside, I can see the stars shining in the Montpellier sky through the glass of the windows in my office. Glass is a solid material, we know that, which differs from crystals in that the molecules in it are in a completely disordered state instead of an organized periodic lattice. But if a glass is a total mess at the molecular scale, so what does it mean for it to be ideal? Can we define the concept of an ideal mess? And what does it mean? And why should we care about it at all? So this is the story that I want to tell you today. So as I started to gather ideas for this talk, I came across these words recently written by the songwriter Nick Cave, whom I love very much. So he said, "The world is not only very good, it's perfect. So wholly perfect that it has the capacity to hold within it profoundly imperfect things like the glass I like to study." And then he adds, "All art is perfectly imperfect, like the world itself." So when I read these words, perfectly imperfect, it reminded me of this notion of an ideal glass, a perfectly disordered state of matter, which sounds like an oxymoron. So when you write articles on glass for the general public, typically editors tend to use illustrations like those, which are pieces of art made of glass. So Venice and Murano in Italy are well-known places where glass making has been developed into an art since the Middle Age. And this is one such example. So today I was reading Le Monde, and Wednesday in Le Monde is the articles about sciences. So I found these pictures of glass pearls. I found them very nice today, so I want to show them to you. It's a picture of glass pearls made around 1400 in Venice, just as I mentioned before, and recently discovered in Alaska. So the article in Le Monde records that 1400 is about a century before Europeans crossed the Atlantic to discover America. And that's the interesting riddle in this article that you can read. So this is not the talk of today. So today it's about those glasses. And so glass today, and I'm trying to show a movie here, it is made just as it was made centuries ago. There are tons of such movies that you can find on YouTube. So the material is heated. It's mostly silica. It's heated above 1300 degrees where it flows as a viscous liquid. And as it cools, it gradually transforms into a solid material, a glass. So the glass makers that we see here, they use this gradual transformation to shape the cooling viscous liquid as they wish. And here, for instance, they want to make it in the shape of a fish. Okay, as in all disciplines, there are world leaders. And it appears that the glassmaker named Lino Tagliapietra, I don't know how to pronounce it, is a leading and inspiring figure in the field of glassmaking. He was born in Murano about 85 years ago, and he says, "Glass is a wonderful material." Why? Because the glass is alive. Even when it's cold, it's still moving. It is connected with fire, it's connected with water, it is so natural. Glass is my life. So I think glass physicists also believe that glass is a wonderful material, and I'll try to show you this in my talk. And it certainly also plays an important role in their lives too. So I will explain in the talk why glass is an important fundamental problem in physics. So Nobel laureate Phil Anderson wrote this in an article which is famous in Science 25 years ago. So the first sentence is like this: "The deepest and most interesting unsolved problem in solid state theory is probably the theory of nature of glass and the glass transition." I think that sentence has probably been cited in very, very many ground applications for people working in disordered systems. More interestingly, perhaps for today, later in the article, he adds the following. He says, the solution of the class problem may also have substantial intellectual spin-off, and whether or not it helps make better classes is questionable. And I think I detect a little bit of irony in these final two sentences. So let me address these two sentences in my introduction for the talk. So first, about intellectual spin-off, I'm totally unsure about what type of spin-off Phil Anderson had in mind. But to me, it seems clear that problems where a large number of objects that interact with each other and are subject to strong constraints that are difficult to simultaneously satisfy are numerous in science. So if you consider these three examples, so you have in the left, you have a dense system of colloidal particles here. In the middle, you have a dense assembly of cells that form a dense biological tissue. And to the right, what you have is you have a dense pile of living ants. And to me, these materials, they all belong to the class problem at large. And indeed, I think that the concept, the ideas, the observables, the models, the microscopic understanding what gets from studying one of these systems often apply to one of the other systems. And this goes even beyond the realm of physics to biology and even computer science. So if you need to be convinced that colloids or cells or ants behave as amorphous solids, let me show you that movie that I borrowed from this paper where they studied the behavior of living ants. So this is the movie I'm showing here. I hope you can see it. So clearly in this movie, you see that this pile of living ants, they are dense, they are disordered, and they look like a pile of a solid material. And yet, if you push on it, then it behaves and responds as an elastic material at the same time. So it's a little bit like these viscous fluids that we are going to talk about. So instead, the liquids that I'm going to talk about today will be composed of atoms and not of ants. But to me, it's a very similar problem. So that's one about the intellectual spin-off and trying to have applications beyond the physics of the glasses. The second part is about making better glasses, and this is my one answer here. Regarding this, there is also hope, I believe. So we've all heard in recent years of the extraordinary LIGO experiment who was recently able to detect gravitational waves. So this is taken from their paper in Nature. So in this interferometer, light is reflected by two mirrors here, which are made of glass. And an important source of noise, which limits the precision of these measurements, is the mechanical loss in layers of amorphous silica and tantalum in these mirrors. So the group of Frances Hellman at UC Berkeley and others are currently trying to develop better glasses, and I will call these glasses ultra-stable glasses, with less defects in them for the future LIGO experiments, using techniques that I will describe only later in the talk. But at least that's one example of why making a better glass is doable and why it's useful. So this is my very, very broad introduction. So let's go into the details of what I want to tell you today. So how to create a glass when we study it in experiments or in the labs or in computer simulations that I do a lot. So just as in the movie that I showed you before, a glass is produced by gradually cooling a liquid like this. So simple substances, usually when you cool them down, they easily crystallize in a crystalline form of matter that I will not discuss anymore in this talk. Just like water freezes into ice at 0 degrees. So here we will be interested in glass-forming substances which do not crystallize easily and remain in a disordered state, in a liquid state that we call a supercooled liquid state in this intermediate regime here. So the liquid becomes increasingly viscous as temperature decreases, as we saw in the movie, which reflects at the macroscopic scale that molecular motion inside the glass becomes extremely difficult and constrained at low temperature, and thus extremely slow. So slow that below temperature that we call the glass transition, the experimental glass transition temperature Tg, that I will use a lot in the following, molecular motion is nearly arrested in that glass state. And the material behaves really as a piece of solid, as we saw in the movie. This is a glass. So the temperature Tg here, it's not really the location of a phase transition. Instead, Tg here is defined by this very simple competition. It's defined by how slowly we cool the system compared to how fast the particles can move. So below Tg, below the experimental glass transition here, particle motion is too slow to occur, and the microscopic structure of the system is essentially frozen. Particles don't move anymore, and the structure doesn't change anymore or extremely slowly only. So to give you numbers at the bottom here, molecular motion in a typical atomic or molecular liquid occurs over a time scale that's about 0.1 nanoseconds, that is 10 to the minus 10 seconds or less. While at the glass transition, it takes something like 100 seconds, 10 to the 2 seconds. So the ratio between these two time scales for molecular glasses is something like 10 to the 12. So 12 orders of magnitude slower at the glass transition as compared to ordinary liquid. So very many people study colloidal particles instead, which are much bigger. And for these particles, the microscopic time scales involved is closer to 1 millisecond, say. So the ratio between my preparation time in the lab, 100 seconds, and the microscopic time scale for colloids, it's something like 10 to the 5. And similarly, when we do computer simulations, we are limited by the capabilities of the computers. And we can again simulate something like 5 orders of magnitude of these slow dynamics in conventional simulations. So we'll come back later over this large gap in time scale, the 7 orders of magnitude between the 5 that you can study in computer generated classes and the 12 you would like to study to compare to real experiments. Okay, so this is how in the computer a glass looks like. So at the particle scale, it's no longer looking like a fish, it's looking like a dense pile of disordered atoms. So this is what it looks at the particle scale. This image here to the right, it's taken from a computer simulation of a 2-dimensional glass forming model. So we see the basic features that I will repeat many times about glasses. They have the mechanical rigidity of crystals, we've seen that, but they have the disordered structure of liquids. In addition, they were produced without crossing any kind of a phase transition. So it's really unclear whether glasses or the glassy phase represent a genuine phase of matter. And given all I've said already, it's not obvious at all what do we mean by the best glass here. So there are many physical properties of glasses that are surprisingly not well understood. So let me mention a shockingly simple one. So since the work of Debye and Einstein more than a century ago, we know that the basic excitations in crystal. They are plane waves and they control all the thermal and mechanical properties at low temperatures in these systems. As a result, we understand, for instance, that the specific heat in crystal increases as the cube of the temperature at low temperature. By contrast, it's been known since the 1970s that the specific heat of glasses doesn't follow the same law. It's linear in the temperature, but we only have a very crude and quite empirical explanation for this behavior. So overall, it means that even basic excitations in glasses are not well understood yet. And this is just one simple example of this type of property and questions that are not well understood. Okay, so how do we make a better glass then? Because I'm after this ideal glass in my title. So I can see two different ways of going. Either we do an experiment where the preparation time is much, much longer, and we increase that preparation and we decrease further this glass transition, this competition between the molecular motion and how fast I can prepare the system. Another way would be to really cool the system there and wait for an enormous amount of time till the system maybe can reach equilibrium at this temperature. The other way that we'll explore as well is be smarter and try and cheat the clock, the timescale problem, and just try and produce a very stable, well-thermalized system in no time at all and be much smarter. So I will explore all these possibilities in the rest of the talk, asking two types of questions. So the first is how and why would you try and do this, which is a practical kind of question. And then I will ask more theoretical question, more conceptual question, asking, for instance, whether there is a fundamental limit to how better I can go in making better glasses. So let's explore quickly the first of these solutions, the wait longer option. So how do you do this? Well, if you want to make very old glasses, take an enormous amount of time to change the properties of glasses, it's probably easy to change your time scale from 1 hour to 1 day, say, and then from 1 day to 1 month of experiments, but then you're stuck because you won't go to years or century. Well, nature can do it for you, perhaps. So these are images of extremely old glasses. So the one on the right is, I think, goes back to the Egyptians. So it's probably 3,000 years old. And it goes back to the time where humankind started to master the art of glass making. So the top left one here is an arrowhead made of obsidian, which is a glass produced directly by nature that men then have used to make arrows. Okay, and the one that I will discuss maybe more is the one at the bottom here with the spider inside. So this is an amber glass. So it's about 100 million years old. So in the last decade, some glass physicists have used a similar type of amber glasses to try and understand how much closer to an ideal glass state they could go using this type of very long aging times. And I'll come back to this later, showing you data. So surprisingly, these experiments seem to show no big differences between 1 day old and 100 million year old amber glasses, which is a bit surprising. So why is it surprising? It's surprising because we all know that if I show you something which is 3 or even 4 times older than another, then you can tell which one is the old and which one is the young object, as in this painting by Da Vinci. If you go to a glass and you look at the particle scale, it's much more difficult to tell the young from the old in these two images. So using a technique that I will describe shortly, the effective preparation time between the configuration in the left and the configuration in the right differ by a factor which is something like 10 to the 10. That means that the configuration on the right has an effective age which is 10 to the 10 times bigger than the configuration on the left. So the question I'm asking to all of you is, can you tell the difference between the two configurations? And can you guess that the preparation times differ by 10 to the 10? It's very difficult, even for glass physicists, I hope. Yet the difference must be hiding somewhere. So is there something in the structure? Are there some kinds of defects hidden in these materials? Are the excitations in these systems different? These are the questions that we ask ourselves when we want to understand the glass transition and the glass problem. So what I hope to convey with these two images is at least try and convince you that giving an answer to what makes a glass and how the structure changes when you make it better are not totally trivial questions, are difficult to answer. Okay, so let's go deeper into it now. Okay. In 1948, the American chemist Walter Kauzmann recognized that something like the ideal glass I mentioned in my title could exist. So this is his historic analysis. It was based on experimental observations. So what Kauzmann did, he collected existing experimental results for a quantity that we now call configurational entropy, and he called it excess entropy, which is essentially the difference of entropy between the supercooled liquids and the entropy of the crystal at the same temperature. So what Kauzmann did in this plot is he used a rescaled version of the evolution of this entropy, and he tried to compare the behavior of this excess entropy or configurational entropy for very many different kinds of supercooled liquids approaching the glass transition. For all of them, what he finds is this very steep decrease of the entropy, the configurational entropy, down to the experimental glass temperature, where essentially experiments stop, because you cannot go below this glass transition temperature and remain in equilibrium. So the liquid does not exist anymore below TG. So these are the data collected by Kauzmann, and Kauzmann's idea was, okay, I cannot do experiments below TG, so what if I just invent the rest of the data and I extrapolate those data to very low temperatures? So what Kauzmann found then is this extrapolation and the fact that there may be something like a critical temperature in this system, a hint of a phase transition at the temperature we now call the Kauzmann transition, where the entropy of the disordered liquid and the entropy of the crystal would be equal, and the difference between the two would then vanish at the Kauzmann temperature. So if we think of entropy as a measure of disorder, it means that we have a disordered liquid state which has as little entropy as a fully ordered crystalline system. So this is the perfectly imperfect state I was mentioning at the beginning, or the ideal glass, as I will call it now. So later, what I will show is I will show recent work on theory, experiment, and simulations, adding quite a bit of support to this idea of an ideal glass. Maybe to finish with the paintings, I don't know whether Salvador Dali was trying to construct an ideal glass here, but his painting contains a rather poor attempt at producing a dense, disordered state of matter in two space dimensions. So this is perhaps he has this funny sentence where he recommends not to fear perfections because we will never reach it. Okay, so let's go more into the quantitative aspect and the theory first. Okay, so what about theory? So the idea that an ideal glass can exist receives both strong support and strong criticisms from people doing theoretical physics. So let's go for the support to get started. Over the last 35 years, roughly, a rather complete mean field theory of the glass transition has been constructed. So this construction started in the mid-1980s through the analysis of spin glass models and received novel momentum a few years ago when the statistical mechanics of glassy systems in the limit of large space dimensions was understood. So this big construction has been recently summarized in a book that has been published last year, and I give the reference here. So it's big, so let me give you just a few very key ideas here for this presentation. So the first message I wanted to convey is that within mean field theory, the thermodynamic glass transition is exactly realized. It has some features of a first order transition with a discontinuous jump of an order parameter, which we call the overlap Q. So let me describe a minute what this overlap Q means. So the definition of an overlap in terms of positions for the particles in the configuration is given in this equation. Let me look at the two snapshots here. So these are two sketches. Okay. So the overlap Q between two configurations of the liquid is defined such as if I take a blue and a red configuration, which are both disordered, and I compare these two configurations, the number Q is defined such that Q will be close to 0 if the two configurations look very different, and this overlap Q will be close to 1 if the two configurations are nearly the same. So the overlap Q quantifies the degree of similarity between two configurations of the system. So why is it a good order parameter to describe the glass transition? So I mentioned before, if you look at the transition between the liquid and the crystal, you just have to look at the structure in a single configuration and you can tell the difference between the liquid and the crystal. If you go and look at glasses, I already told you that it's really difficult to distinguish the liquid from the glass just by the eye, just by looking at the packings. So the wrong question to ask is, how do glass packings look like? They all look the same. I mean, I confused you with my two configurations before. Okay. So the better question to ask is the one at the bottom here. And so the question is, how many distinct packings are there? So in the liquid, there are very many accessible configurations. They're all distinct, they're all disordered. So if I take 3 configurations, the red, the white, and the blue in the liquid, they all look different, they all look disordered. So if I compare them using my overlap I defined in the previous slide, they all look different, so the overlap between them will be small. So in the liquid, the overlap between configurations is 0. By contrast, if I'm in a glass and I have very few accessible configurations, if I compare the red, the white, and the blue in the glass, they all look the same roughly, and so the overlap between them will be quite large. So the order parameter is how different the packings I can access, how different are these packings. So if you remember also that entropy is a way to enumerate the number of accessible configurations in the system, then you see that you start to see why a glass phase with a large overlap, like in this snapshot here, also has a very low configurational entropy because very few configurations can be accessed for it. So I try to define and give you a feeling for what this overlap means and why it's the good order parameter to describe the glass transition. So it's such a good order parameter that it's possible to rephrase the mean field theory of the glass transition in the language of conventional phase transitions, expressing, for instance, the free energy as a function of the overlap, just as in conventional Landau descriptions of phase transition. So this is what I'm showing you in this plot here. And this Landau free energy in the context of glass physics has received the name of the Franz-Parisi potential V of Q. Okay, so the behavior of this free energy as a function of the order parameter is shown here for a specific mean field glass model. And it has the behavior expected near a first order transition. So you see these two minima that whose relative stability is changing as you change the temperature. So above the glass transition, the glass phase at large overlap is metastable with respect to the liquid. And both phases then have the same free energy at the Kauzmann transition Tk. And below, at low temperature, it's the glass which is the most stable state. So we can show that the free energy difference between the liquid and the glass is directly related to the configurational entropy I mentioned before. So this configurational entropy is going to vanish continuously as we approach this temperature Tk. At the same time, the stable phase is the liquid with the small overlap. And at the glass transition, the overlap is going to jump discontinuously to this new minimum. And so the overlap is going to jump and increase discontinuously across Tk. So this is the mean field picture of the glass transition. Okay, and indeed what I hope you see is that the configurational entropy in this mean field approach, which is valid, as I said, for liquids in large dimensions, realizes exactly the scenario imagined by Kauzmann 70 years ago. So in a sense, The situation is very clear at the mean field level. We have this first order phase transition, which occurs at a finite Kauzmann temperature to an ideal glass phase that exists in this mean field limit. And the transition and the glass phase have known properties. So in a sense, the quest that I mentioned is my title, the quest of an ideal glass. It's over, but it's over only in the mean field limit. For instance, in the limit of a large number of space dimensions. Still, there remains many physical consequences to explore within the framework of mean field calculations, and it's still an active field of research. Clearly, however, the next challenge is to try and treat analytically the fluctuations that will necessarily occur when we go down in dimensions. And anything can happen between small changes to the mean field picture to a complete destruction of this construction. Okay, so how do we go down in dimensions? How do we create better glasses in finite dimensions? So to make progress there, one needs to explore smarter ways of making glasses. So I already mentioned the wait longer alternative. So here is an example of the be smarter approach, where glasses are produced here using a process called physical vapor deposition, which I'm sketching here. So in this process, molecules in the vapor are slowly deposited on this growing substrate here to produce glassy films. So the control parameters are obvious in this protocol. So you can control the deposition temperature of your process, and you can control how fast or how slowly the molecules are deposited on your substrate. So here the analogy with the game Tetris suggests that if you pile your molecules very, very quickly, it will be difficult to have an efficient way of packing them. And on the other hand, if you pack them rather slowly, the molecules may have time to reorganize themselves in a much better way as compared to when they arrive fast. So for well-chosen parameters that I won't discuss here, but were essentially discovered in this work published in 2007 by the group of Mark Ediger, the University of Madison, Wisconsin, amorphous materials behaving as million-year-old glaciers have been produced in just a few hours. So this is just one way of beating the timescale problem. So is this useful? Well, I think over the last 14 years, the group of Mark Ediger and now several other groups all over the world have worked very hard to demonstrate that these new types of glasses that they have called ultra-stable glasses, they have different and interesting physical properties for both fundamental questions that I will address later and practical applications. So it is, for instance, the method that the group of Frances Hellman is trying to use to develop the better mirrors of the LIGO experiment I mentioned in the introduction. So here I'm just showing you one specific example of a practical application where these new types of glasses could be useful. So this is an experiment that has been done in part in the group of Rodriguez Viero in Barcelona, who constructed this schematic thing. It looks complicated, but I think as far as I understand this paper, it's a lab version of the complicated OLED display, which is used commonly in many smartphones. For instance, the ones that are constructed by Samsung, as I understand. So what they demonstrate in this paper is that if you make some of these layers in this very complicated OLED display ultra stable by using the vapor deposition procedure I mentioned before, if you make them better glasses, you can improve both the lifetime and the efficiency of this OLED display. And they have shown convincingly that this is due to the better packing of the vapor deposited amorphous films. So this is one example of a practical application. Okay, so these are experiments. So can we do better computer glasses now, and this is what I'm going to discuss. So just for experiments, it's difficult to increase significantly the duration of a computer simulations. And as compared to experiments, computers did not exist millions of years ago. So we cannot use nature to have very old computer glasses. So recently, a simple Monte Carlo algorithm was devised to very efficiently prepare computer glasses that would take an impossibly large time to prepare using conventional methods. So the method is super simple. It's sketched in this cartoon on the right. It amounts to frequently exchanging the identity of pairs of randomly chosen particles in the system. So you take the two deep blue particles and you exchange their identity. You do this frequently throughout the system, and that's it. This is the algorithm. So the performances of the algorithm can be optimized to provide a very big equilibration speedup, as shown in the main panel here. So this is what I'm going to explain in a minute. So as I told you at the beginning, if we use conventional computer simulation and we follow the physical dynamics of the system, we can cover something like 5 orders of magnitude of glassy slowdown given the computer capabilities that we have. So we are well short of the 12 orders of magnitude that are needed to reach the experimental glass transition TG that I defined earlier. So what we can say is that when the swap Monte Carlo moves are turned on, this is the time it takes to equilibrate the system on the computer. And the equilibration becomes so fast that it takes something like 10 to the 2 or 10 to the 3 steps here of the simulation to equilibrate the system at a temperature which is equivalent to the experimental glass transition. So it means that the type of speedup that you have at the experimental glass transition, it's at least as large as 10 to the 10 for these 3-dimensional glasses. We've done simulations in 2 dimensions where the estimated speedup is ridiculously large, something like 10 to the 40, which is, when converted in physical unit, means that we have prepared in the computer glasses that are much, much older by orders of magnitude as compared to the age of the universe. So this is the speedup that we get from by using this swap Monte Carlo algorithm. So is this useful? Well, depends on what you call useful. So it's not possible to apply this trick to experimental work yet. So it's not practically useful for industrial applications yet. But for glass research, I would say it certainly is extremely useful. So first, it means that the very big timescale gap between simulation and standard experiment is totally closed. It's in just one go like this. We believe we can simulate ultra-stable glasses similar to the kind of vapor deposited glasses I mentioned before. And so hopefully we can approach nearly ideal glasses like this one. So clearly it's having this new tool means that it's a very exciting moment for doing glass physics, as it gives us a new handle to address the key questions in the field. Quick questions regarding finite dimensional glasses in close connection to both the theoretical developments I mentioned before and the novel experiments that I just mentioned as well. So it's very nice to be in between those 2 things. So it means that we can try and get a first glimpse of the perfectly imperfect or the nearly ideal molecular packings. So this is what I'll do in the rest of this talk. I will show you a few results regarding the existence of this ideal glass I mentioned several times, but also the physical properties of glasses that are really pushed toward this limit, prepared over a very wide range of glass stabilities, from the ordinary computer glasses to the nearly ideal ones that we can now study in the computer. So this is what I'll do now. So the first question we want to address is, the question of the very existence of an equilibrium phase transition, of an equilibrium glassy phase of matter, based on the insight provided by the theory of the glass that I mentioned before. So here what I show are the results of the simulations where the central quantity I mentioned before, this lambda free energy, this Franz-Parisi potential B of Q, can now be measured in computer simulation. So this is the simulation of a three-dimensional system. It's still quite demanding. It's not totally straightforward, but it's now manageable. So the figure shows the evolution of this free energy for a three-dimensional system as the system approaches the glass transition, and we go as far as we can. So we remain above the glass transition, but we approach it considerably closer than before. So what these data reveal is essentially the development at large overlap of this metastable glass phase that was predicted in the theoretical pictures I mentioned before at low temperature. So this type of study represents, in a sense, the direct signature of this coming first order phase transition that is predicted by the mean field theory. This transition between the liquid and the glass at large Q values here. So what about the work of Kauzmann itself? Can we revisit it and say something? So similarly to Kauzmann, we can collect the new data obtained from the physical vapor deposited glasses and the new computer simulations to look at the behavior of this configurational entropy in various supercooled liquids. So the gray symbols here are the old literature data, the ones that Kauzmann had used 70 years ago, made more precise by newer experiments, but essentially the data look the same. So there are novel data in this. So first of all, you can see this circle here. These circles have been estimated using the vapor deposited glasses I mentioned before. And as you can see, I mean, these data go much, much closer to the Kauzmann temperature as compared to the 70 years old data of Kauzmann. So the new thing, of course, here are the colored data. These are the results of computer simulations that I want to highlight now. So what we have is essentially the same behavior in these three types of system as the experimental system. So these red, pink, and blue data are three types of computer models that we have studied in the computer. And you can see that for the blue ones, for instance, we directly compete with the level of stability that the vapor deposited glasses have obtained. So there is one guy here which is a little bit different, which is the green one. So the data here are obtained for a glass simulated in 2 space dimensions. So clearly it behaves differently from the others. So the data suggests that if you do the Kauzmann extrapolation of where this entropy is going to vanish, it's going to vanish very close to 0 temperature, suggesting that this ideal glass phase where the system transforms into a glass, it does not exist for 2-dimensional systems. So it seems maybe that Salvador Dali was right after all when he claimed that perfection would never be reached. At least he was right in 2 dimensions. So let me go over this next slide. So mean field theory predicts that close to the Kauzmann transition, the glass phase at large overlap is metastable with respect to the liquid. So by analogy with other phase transitions of first order nature, this suggests that if I introduce a field conjugate to the overlap, conjugate to the order parameter, I should be able to induce something like a first order phase transition by making the glass phase at large Q the stable phase. So I will call epsilon that field, and what I'm now considering is, in a sense, an extended phase diagram where instead of having only temperature, I have temperature and this new field epsilon now to explore. So this is the sketch of the exploration of the phase diagram. So we've I've described to you before what happens on the vertical axis when I don't introduce this artificial field. And the theory predicts this transition between the liquid and the glass at the Kauzmann transition. So now we have a whole new plane to explore in the presence of this epsilon field. And what theory predicts is that out of this metastable glass phase here will emerge a line of first order transition here at finite epsilon, ending at a new critical point here at a finite temperature and finite value of the field. So this blue line here is the direct consequence of the metastable nature of the glass just above the Kauzmann transition here in the theory. So in recent years, this computer simulations technique that I mentioned, for three-dimensional glasses, they have shown that this predicted critical point exists. They have determined its universality class. They have been able to follow the blue line over a broad range of temperatures. And this is illustrated just briefly in this figure here. So here what we do is we follow the increase of the overlap as a function of this field epsilon. So we have a smooth increase of the overlap at high temperature because we go above this critical point here. And when we cross this blue line here, we have a discontinuous jump of the overlap across this first order transition blue line. So these results show that the entire thermodynamic construction associated to the existence of an ideal glass phase, it can be rather convincingly observed in three-dimensional systems. So what remains to be observed directly is the Kauzmann transition point itself. So we can approach very close in temperature, we can approach very close at finite epsilon, but we need to close this gap here with this Kauzmann point, and we haven't been able to do so at the moment. So maybe I'll skip that one. So let me go deeper into the some of the physical properties of glasses, echoing the questions that I mentioned in the introduction. So one thing I mentioned in the intro was that even the basic excitations, even at the harmonic level in glasses, were not well understood. So in recent years, it was shown that harmonic excitations in glasses at low frequencies can be understood as the superposition of ordinary plane wave excitations, just as in crystals. So that part is relatively understood. But there is a new population of quasi-localized harmonic excitation, which is described by this density of state, which increases as the fourth power of the density. So the Debye density of state for crystals would increase as omega to the d-1. So it's different from the Debye plane waves. So it was also shown using these tools that I introduced, this swap Monte Carlo algorithm, that if we follow the evolution of this quasi-localized mode as the preparation time of the glasses increases as we prepare better and better glasses, these excitations are strongly depleted when we increase the stability of the glass. And this is shown here where this prefactor in the density of state is shown as a function of the preparation, the equilibration temperature of these glasses. So we see that this prefactor, which was relatively high at high temperature, decreases sharply as the temperature decreases and almost vanishes at extremely low temperature. So we may suspect or hint or conjecture that maybe these quasi-localized harmonic excitations are going to disappear when we approach nearly ideal glasses. So this is the excitations at the harmonic level. I want to discuss now mechanical properties of glasses quite briefly. That is, how a glass responds to a mechanical deformation. So again, it's now well understood that plastic deformation in glasses systems, it's carried by something looking like localized defects again. So it means that when a glass is very slowly deformed, there are very small regions in the material that carry the entire plasticity. So it means you have large molecular rearrangements in these light blue spots in the system, in the middle of a deep blue sea here where the system responds like an elastic system. So this is what this illustration means. You have these few localized defects that carry the plasticity and that allow the mechanical deformation of the system. So again, in these computer simulations, trying to change and approach glasses that are extremely close to something that I like to call the ideal glass phase in this talk. We have studied how the mechanical response of glasses changes from ordinary computer systems to ultra-stable ones that we can now prepare using the Monte Carlo algorithm I mentioned before. So what we again discovered in this simulation is a strong depletion of these plasticity defects that I mentioned. And I will show two movies to tell you the difference between a system that has been poorly annealed and a system that's extremely stable. And you'll see the difference in the mechanical response between these two systems. So let me start with a system that is badly prepared, low stability, full of defects. And this is how the system will look like. So I will stop just in a minute. So this is a computer simulation of a glass that is being deformed. The highlighted particle means particles that have undergone some kind of reorganization in the system. And the deep blue color means that essentially the system is deforming affinely with the deformation. So if I try to make the movie happens and I stop it again later, you see that this system is full of defects. So there are many locations in this system where the system has reorganized. And this is allowing the slow, gradual deformation of this glass sample. So I stop again at very large deformations, and plasticity occurred everywhere in this system. I will now go to a very stable system, and I will show you how this system is deformed. So this is the initial state of the system. So it's very deep blue at the beginning when nobody has relaxed. I deform that system quite a bit more, and I will stop later. So I stop here, for instance. So we see that we have deformed that glass quite a bit. And by contrast to the system that was full of defects, almost nothing happened here. It's still a deep blue, almost elastic system. So what happens? What happens if you deform this glass further is something dramatic. It's something like this. We have an avalanche of plasticity that takes the form of this fracture in the system. So unsurprisingly, if you know what the glass does when you deform, here this system is completely breaking. So to summarize, we have illustrated in these two movies the fact that when we increase the stability of glasses by approaching this ideal glass type more and more, when we increase the preparation time of the system, when we make those systems less and less disordered, we have a dramatic change in the way these glasses deform from a smooth, gradual plastic deformation of glasses to something that breaks like real glasses do. So we conclude by saying that the transition between a smooth deformation and catastrophic failure where the glass breaks, it's directly controlled by how stable, how defective the system is initially. So is this useful? Is this property useful? Why, yes and no. So it at least suggests that if we push this towards the ideal glass that I'm mentioning all along this presentation, the ideal glass should be extremely hard, but at the same time, it should be extremely brittle. So probably producing very hard glassy films could be useful for some applications. But on the other hand, some experimentalists in the field are not liking when their sample is breaking. So for instance, there is a large community of people working on metallic glasses, and they try to do the exact opposite of what I'm trying to do in my talk. They try to increase the disorder. they try to move away from an ideal glass to have a deformation that is not brittle, to have a system that is not breaking into two pieces, as in this system, but something that deforms more plastically, as in this example. So this is an example of a paper that I took last year from metallic glass experiments, where really the experimentalists try hard to rejuvenate the system to make it more disorder, less ideal, because this system doesn't break easily under deformation. So I'll finish with the last story, trying to conclude and loop with the very low temperature properties, and mention again this very old amber glass experiment. So I go now to extremely low temperature properties, and I mentioned in the introduction the anomalous behavior of the specific heat of glasses that increases linearly with temperature as compared to the cubic behavior observed in glasses. So to detect this linear versus the cubic behavior of crystals, experimentalists typically plot Cp divided by T cube, so that the crystal would behave as a flat horizontal line here, and glasses would then have a diverging 1/T squared behavior at low T. So I mentioned before this anomaly in the specific heat of glasses that's been known since the 1970s. So this behavior has been explained or rationalized by invoking the existence of, again, a finite concentration of localized tunneling two-state systems, so two-level systems, TLS in short, with quasi-generate energy levels. And these types of localized defects in glasses would directly explain the linear specific heat behavior of glasses. So the Anderson in this list is the same Phil Anderson that I quoted in my introduction. So what about new experiments using these very old amber glasses or these very stable vapor deposited glasses? So these two types of systems have been studied at this very low temperature. The specific heat has been measured. And these two types of experiments offer conflicting views on the behavior of these localized two-level system defects in glasses. This experiment on the left is performed with the 100-million-year-old amber glass. So one of them is the 100 million years old amber, and one of them has been heated and then cooled down in just a few minutes. And essentially the specific heat is the same. So the very old glass behaves just as the very young glass for amber. On the other hand, if you compare conventional glasses and vapor deposited glasses for the same substances, the ordinary glasses have the linear T dependence as in ordinary glasses, but the vapor deposited glasses have this horizontal behavior, so the T cube behavior of crystals. So in one case, we would conclude that stability removes the two-level systems, the defects. And for the amber, we would say that stability doesn't know about these defects. So what I'm showing, and this is almost my last slide. So we have used, again, computer simulations using the swap Monte Carlo algorithm to address this question in simple models in the computer. So we have been able to directly estimate in this model how the density of tunneling two-level system is changing by changing the stability of the glass from very stable to poorly annealed systems. And this is the main result of this analysis. We find a very strong reduction in the density of two-level system by about 100, a factor 10 to the 2. So 2 orders of magnitude depletion of the total number of these two-level systems in the glass as we go towards more stable system, towards this vapor deposited system. So the results we have are in agreement with at least one of the experiments. So to us, it's the behavior of the very old amber glass which remains a puzzle that we don't explain and doesn't look like the simulations we've done. So is this practically useful? And this is my last slide, Sid. So the two-level system, as I said, they dominate the dissipation in amorphous solids at extremely low cryogenic temperatures. So one application where maybe this would be useful to remove these two-level defect systems is quantum computers. So I'm not an expert here, but I've read a few papers on them. And they have demonstrated in these studies that the qubits that are made in some of these in these quantum computers, they may interact with the amorphous structure that make them, these two-level systems. And this is a source of decoherence in these quantum computers. So this is an image that I took from the Google quantum computer paper 2 years ago. Okay, so I started by quoting the glass maker Lino Tagliapietra, who said that glass is a wonderful material. I hope you enjoyed the ride with this material. I've tried to explain that what makes glass is interesting is this duality between the liquid-like disordered structure that I mentioned several times and the solid-like behavior. So when I look at this highly sinuous and tortured painting of the Russian painter Sutin, I find that the glass in this painting, the bottle in this painting, the lamp, I think they do capture this liquid-solid duality quite well. And also looking at this painting, I find that it looks like a lovely illustration of the Nick Cave statement that all art is perfectly imperfect. So I thank you for your attention.